for inviting me to this beautiful venue, and it's really a pleasure to be here. So, as Simeon said, I will be speaking about the uniqueness of Landau levels, and more precisely, I will be speaking about the uniqueness of lowest Landau level Bloch wave functions and their analogs with higher Chern numbers. So this work here was developed at IMR, Advanced Institute for Materials Research at Tohoku University in Japan. And recently, since May, I will start a position in Lisbon in this institute, Instituto de Telecomunicações, also affiliated with Instituto Superior Técnico, Universidade de Lisboa. Okay, so let's move on. So this is the outline for my talk. Okay, so first I will be giving somehow my perspective on Bloch bands and quantum geometry. And then I will be speaking about a concept that we have introduced recently, which is that of Kähler bands, a specific type of Bloch bands, of which the lowest Landau levels are examples of. And then I will particularize to the case of ideal Kähler bands, which are also known as ideal flat bands in the literature. And then I will particularize even further to the case of flat Kähler bands. So this notion of Kählericity seems to find a lot of interest recently. Because of problems related to the stabilization of fractional Hall phases in lattices. And in particular, there's some kind of condition in the quantum geometry that it really leads to a Kähler band, and in particular to flat Kähler bands, first originally understood. But by some works of people in the audience, it's now known that actually what you need is just ideal Kähler bands or ideal flat bands. So let me move on. Okay, so Bloch bands and quantum geometry. So here I will try to abstract the concept of a Bloch wave function. So first let us consider a real space lattice, the real space lattice Z2 in R2. And then the reciprocal lattice is again Z2, which is the momentum space lattice. So I will be also denoting elements of this lattice here by capital R. Okay, so and elements of this lattice here by capital G's. So if you see those letters, you know what I'm talking about. Okay, so definition, Bloch wave function. So this will be what I mean by a Bloch wave function in this talk. So for me, a Bloch wave function, specifically in 2 dimensions, is determined by a family of non-vanishing vectors, use of k, on a fixed Hilbert space, Matkal H, smoothly parametrized by k in R2, which will be, R2 will be the universal cover of my Brillouin zone, and satisfying this quasi-periodicity relation. So I will require, so okay, here is the quasi-momentum, okay? So I will require that my use of k plus g is in the reciprocal lattice, is related to use of k by 2 things. The first thing is this quantity here is of g of k. So here this is a non-vanishing complex number. And then I have another quantity here, which is this use of g, which is a unitary operator. And I will demand that these EGs of k form, as you consider the whole family of them in terms of reciprocal lattice, is a system of multipliers for a line bundle, L over the Riemann zone. And let me just, oh, sorry. And this U sub G is a unitary representation of the reciprocal lattice. So first, let me just say briefly what is a system of multipliers for a line bundle. Is this okay? Yeah. It's just. So the only thing that I require. Sorry, I'm a bit short. So this is like a co-cycle condition. And so this is, yes?
So does it mean that you have a projective representation of your dual lattice? Or
I think
the separation into E and U is...
I can't tell you for sure, but it seems to be something similar. Okay, so this here just means that where this means that I consider pairs and I identify them by the action of the reciprocal lattice like this. But I don't want to say yes because I'm not sure, but it seems related. Yes. Okay, I can move on. So we have this relation here, this definition. So I would like to make some remarks on the definition. So first, L has a natural Hermitian inner product and a compatible connection. And you might find it weird that I put like this, but this is just that if you take a section of L and make the modulus squared and multiply it by this, you'll get an invariant function. And the connection. And compatibility just follows from, if you take the derivative of the logarithm of this quantity, you'll find that it is the real part of A. And because of this, L is not just a line bundle, it is an Hermitian line bundle with connection. And this is very good news.
One quick question.
Oh,
the base is a torus or it's a whole plane?
The base is the torus. So yeah, exactly. But since you have this formulation here, you can think in terms of, if you want to think about sections of L or things like that, you can think in terms of the universal cover, which is convenient. So you can think of sections of L as quasi-periodic. So you can think of sections of L as functions from R2 to C that satisfy this relation here. Okay, this is one. So if the function, if you have a function from R2 to C that satisfies this relation here, then it determines section of L. Okay, good. This will be important for later. Okay. Good. Okay. So now I want to introduce equivalence relation, because I don't want to think everything is equivalent. Everything is different. So two families, U sub k and U sub k prime in the same given Hilbert space, are said to determine equivalent block wave functions if there exists a smooth function, G, from R2 to the invertible complex numbers, such that this relation holds. Okay? And the remark on this definition.
Sorry, why is it not allowed to do a unitary?
I will get there. I will get there. So this transformation induces transformations of the multipliers, and this transformation is simply producing isomorphisms of line bundles. So if I have two line bundles, they give the same, and they are isomorphic, they give the same block wave function. And now, going back to your comment, perhaps a weaker and more general definition of equivalence would be two families UK use prime k in the same given Hilbert space are said to determine equivalent block wave functions if there exists smooth function and constant, this is important, constant unitary operator such that this holds. And U has to be constant, otherwise you'll see that things will fail. Okay, so let us move on. Another remark is that this unitary operator intertwines between the unitary representations, and this is important also. Okay, move on. And now I want to talk a bit about spatial structure of block wave functions, because right now I didn't mention any spatial structure. And this will turn out to be related to the characters of the lattice. So since UG determines unitary representation of Z2, I can split it into unitary haps. And the unitary haps of reciprocal lattice are labeled by these characters, which are group homomorphisms of Z2 to U1. And they are labeled by points in real unit cell because you can write them like this, and you see that if I take R and I sum with a capital R in the real space lattice, I get back the same character. Okay? So the real space structure of block wave function will come once I decompose my representation into irreducibles. Okay? Continue. And then what happens is that, I split my Hilbert space into a direct sum where this unitary acts on each factor by character. Okay? Remark. The direct sum is over a collection of points in the unit cell, so the little rectangle in R2. So you choose, there are some points here that appear depending on how many E-reps that appear. And this collection can be the whole unit cell, and in that case the direct sum has to be replaced by more general direct integral. This is a bit of a formality, but it's important. Continue. Quasi-periodicity condition. So now, suppose I split my block wave function in terms of irreducibles. This is the irreducible component in H of R. Okay. Then this guy satisfies new quasi-periodicity condition, which now is affected by character. So effectively, you see that there is a twisting of my original line bundle by the flat line bundle corresponding to this character. It will appear later, but I'm just spoiling you a bit. So I continue a bit more. So fix an orthonormal basis for the HR. I don't know what is the dimension, so I just label it like this. And I write this in terms of components. And from the definition of block wave function and the previous quasi-periodicity condition, you find that these functions, the coefficients, satisfy this relation, and therefore they determine sections not of L, but of L tensored with a line bundle, a flat line bundle. But let me just say this. So they determine sections of a new line bundle, L sub R, over real one zone 2, BZ2, whose multipliers are not EG, but are EG of K times the character. Okay? For each R occurring in the decomposition, we have one such line bundle. So now we have a collection of line bundles labeled by points in the unit cell. As many points as irreducible representations of U we find. Geometric interpretation. So the positions in R determine the characters, and they define flat line bundles like this. So this means that you have the trivial line bundle over R2, and you have a Z2 action given by translation in the first factor and the second multiplication by the character and your quotient. And this twist, so L sub R is essentially the tensor product of L by this flat line bundle. Okay, that's what I wanted to say. And now this tells us that the UK sub R, they know of the spatial structure of the unit cell through the holonomy on fundamental loops of the Brillouin zone of this form. So you take a reciprocal lattice factor and you consider these curves. This span these fundamental curves. And the holonomy contribution from the flat factor is precisely the character of the irreducible representation with a minus one. So this is the only picture I have in this talk. I apologize for that. But so we have point in unit cell. We have fundamental loop as described by reciprocal lattice vector, and you get the holonomy, which is the character. Okay, very good. We continue. So now I want to talk a bit about quantum geometry, which has been a very recurrent topic lately, especially because it seems that not only the topological side of these block bundles are important, but also geometric features can be important. So it is important to understand very well what this means. So we have this assignment that for each k in R2, I assign U sub k in the Hilbert space minus the origin. And these, if you take the quotient here by the C star action on H minus O minus the origin, you get a map from R2 to the projectivization of the Hilbert space, and this uniquely determines the Bloch wave function. And this space here, P sub H, is possibly infinite dimensional Kähler manifold, and it's infinite dimensional, or it's scalar manifold with respect to Fubini-Studi Kähler structure. So this Hilbert space comes with inner product, and this gives you a Kähler, induces Kähler structure on the projectivization. So here I denote the Kähler structure by the pair, because this is a complex manifold, and this is symplectic form. They are compatible, and the Fubini-Studi metric just comes from this relation.
I'm sorry, I have a question, Bruno.
Oh, please.
So, yeah, in your case, what parameters in your model determine the fact that pH is finite dimensional or infinite dimensional? And when finite dimensional, do you have a way to compute its dimension, or is it purely general?
As I put the definition in the first slides, I said that there was a fixed Hilbert space H. Yeah. The dimension of this
you provide the model with a Hilbert space. It's not computed explicitly from the parameters. Okay.
Very good. Over P sub H, we have a Hermitian holomorphic line bundle known as the tautological line bundle. It is the line bundle whose fiber over the line is the line itself. Is this clear? Okay. And its Chern connection has curvature 2 times I, the symplectic form of the Kähler manifold. Okay. Definition: Berry curvature in quantum metric. The Berry curvature F and the quantum metric G of the Bloch wave function determined by U sub k are, respectively, the pullback. F is the pullback of 2i omega fs. Therefore, is the curvature of the pullback bundle. So you use that map to pull back the tautological line bundle, and you get F. And G is the pullback of Fubini study. Okay.
Excuse me, pullback with respect to which map?
F.
What is F? Ah, okay. So,
Good. Proposition the tensors F. Right now, my map F was from R2 to piece of H. And G, which is the metric, they go down to the quotient. And this boils down because of the way I carefully handled the definition. Because, and not only that, the tensors F and G only depend on the Bloch wave function, the equivalence class, not the representative. So under the equivalence that I gave you, this is well defined. So the proof is very simple. If you recall from my definition, I had this, and then consider the diffeomorphism, which comes from K, goes to K plus G in the G reciprocal lattice vector. Then we have that the composition of F with phi G is given by the induced map coming from unitary, which depends only on G and does not depend on K with F. Yes. And the thing is that Fubini study since there are many boards, I might as well take advantage of that. And if I have these two things and I take P and P only depends on K, you see that these formulas are invariant, because this does not, when I take derivative with respect to K, this thing does not appear, and trace is invariant under conjugation. Good. And of course, the same. You can also. Well, the same holds by multiplication by the. Okay. This is good. And the second. What I wanted to say is that this unitary is essentially an automorphism of the Kähler manifold, and this holds. And the second part, because the way I stated equivalence is again the equivalence is done through automorphisms of the Kähler manifold, and therefore this thing holds. Okay. So, any question?
Of a projective space, not a manifold, not a K manifold.
The projective, complex projective space is the only Kähler manifold that appears to appear for the time being.
Right now, yes.
K space, right? You pull back some.
Kilometric. Yes. So use of G is automorphism, and when I act with use of G, since I'm pulling back, this holds. So there's this intertwining. So if I take pullback, if I use pullback in this formula, I get the pullback reshuffles order, and therefore good. Okay. So now we go to different Kähler manifolds that will arise. Kähler bands. Okay, so definition, Kähler band. So a Kähler band is determined by a Bloch wave function. So we are in the same setup as before, but now the map F is a holomorphic immersion with respect to a complex structure J that is invariant under reciprocal lattice translations. So I'm requiring this last thing, that J has to be invariant under reciprocal lattice translations, because eventually I want to go to the torus, right? Okay. Remark, for a Kähler band, this triple of structures, F star of omega Fs, F star of GFS, and J, this determines, this is a Kähler triple, and determines a Kähler structure in the Brillouin zone, and hence the adjective Kähler.
So J sits on what? On the R2 or?
J is a complex, right now, is a complex structure on R2, right? And this map has to satisfy, so I have a map from R2 to the projectivization of H, and R2 is equipped, sorry, I have no way to erase, with H, and this carries the Fubini-Study complex structure, and there's a commutativity. So this map is holomorphic. Okay, so we have the adjective Kähler. So right now the Brillouin zone has become a Kähler manifold. So now I'm going to go a bit even more restrictive, which is that of ideal Kähler bands, and this is exactly what happens in TPA, in twisted bilayer graphene. So definition, ideal Kähler band. Ideal Kähler bands, also known as ideal flat bands, are Kähler bands with respect to translation invariant complex structures. So now, besides requiring that J is invariant under reciprocal lattice translation, so that it goes down to the quotient, to the torus, I also require that it is translation invariant, fully translation invariant. And such complex structures are determined by modular parameter in the upper half space, and you can think of it in terms of complex coordinate in the universal cover, kx plus tau ky. Okay.
Excuse me, short question. Physical example. Suppose I have a layer, magnetic field up, and then another layer, magnetic field down, total 0. I connect them. Could it be an example of?
An example of an ideal Kähler band. So an example of a Kähler band is the lowest Landau level. The lowest Landau level, because of magnetic translation, is even better than that. It's a flat Kähler band. So you will have that Berry curvature is translation invariant, quantum metric is translation invariant, and the complex structure is induced from the complex structure that you have in real space that comes from the mass tensor that you have on your problem. So in this isotropic case, it's just tau equals to I. So that's an example.
Could it be realized in terms of some combination of layers in quantum complex?
So it is realized in terms of the lowest Landau level wave function. It's also realized in twisted bilayer graphene. There, just the quantum geometry is not flat, but it is that of an ideal Kähler band. That's known. Good. So, because we are in the holomorphic domain, I should talk a bit about structure theory, which is more simple. So, the holomorphicity condition in terms of these representatives use of K is written in this way, here. But if you use a holomorphic gauge, then you can basically reduce to this simple equation. And we can then assume that the multipliers are holomorphic functions. And I will take gamma to denote elements of reciprocal lattice, like this. And what happens is that this line bundle, L, that I had in the start, is no longer just a smooth line bundle, but it comes equipped with the structure, well, no longer just a Hermitian line bundle with connection, but it's an Hermitian holomorphic line bundle. And in fact, this is the same for all the Ls of R, because Ls of Rs are just twisting by flat line bundles, which are holomorphic. Good. So holomorphic line bundles over complex tori are always isomorphic to holomorphic line bundles, isomorphic in holomorphic category, to holomorphic line bundles whose holomorphic sections are described by suitable theta functions. So just a small reminder, these are theta functions. So I learned a lot about this on Simeon's notes on theta functions. So this is theta function with characteristics A and B, and it's given by this absolutely convergent sum. And the parameter tau appears here, and you see that I since tau has positive imaginary part. This is damping Gaussian. We may assume that after multiplying, remember that we had an equivalence degree of freedom, which would produce isomorphic line bundles. I can multiply by g sub k and assume that the multipliers assume this beautiful canonical form in such a way that I will recover precisely these theta functions. And here, in this expression, you see that there appears a c. C here is a positive integer, and it is the degree or Chern number of this line bundle L sub R. And it's also, mathematically, it's the dimension of the space of holomorphic sections of the line bundle L sub R. So don't forget what little math C is. So, and then, because of that, because the f of alphas will have to be holomorphic sections, then the only possibility for is that they are linear combinations of these theta functions, which span this vector space, which is the finite dimensional of dimension c. So we reach the following conclusion, which is the structure theory of ideal ideal Kähler bands, which is for an ideal Kähler band with flat complex structure specified by modular parameter tau and Chern number c, we have this direct sum, the composition, direct integral. And once you fix basis of this Hilbert space H of R, then these f of alphas are determined sections of these L sub R's, and they are of this form, with possible still residual dependence in R here. This is important. This residual dependence in R is still there. Okay, I'll make more comments on that later. And this, they actually depend on the particular ideal Kähler band, and they also depend on the particular choice of bases we've chosen for the H of R's. Okay, so now we are going, we're going conical to something more and more restricted. And right now, before the f of alphas were just sections of some smooth sections of line bundles, and these spaces are very wild. But now we are in the holomorphic domain, and this highly constrained us to the coefficients that are highly constrained. Okay, we continue, and now we go even further, and we talk.
Sorry, one quick question. What were x and y again?
X and y. Very good point. It's the coordinates in here, in R2. Because remember that little r labeled the point in unit cell. So
It's a real space.
It's real space coordinates. Yeah. Very good question. Yes. So this f of alphas, they have the label alpha, which corresponds to the basis in H of R, and they have another label R, which has to do with the character corresponding to the position in the unit cell. Okay.
So when you write z, it's k.
When I write z is kx plus tau ky. Yes, exactly. Yeah. So now we move a bit further. We go to flat Kähler bands. Oh, it's passing fast. Flat Kähler bands. So flat Kähler bands are Kähler bands for which not only the complex structure is translation invariant, but the whole quantum geometry is translation invariant. So I require metric to be translation invariant. I require Berry curvature to be translation invariant. Everything is translation invariant. Consequences of definition. For every Q in R2, I have an induced diffeomorphism in Brillouin zone, by that, tautological. And translation invariance of quantum geometry means that I have these pullbacks that preserve the geometric structures. And having this equation, I can associate to phi q an isometry of the Fubini metric, which then leads to H to act as a unitary or anti-unitary operator use of Q. And this is like an instance of Wigner's theorem that the quantum symmetries, which essentially have been shown to be isometries of the Fubini metric, are represented in Hilbert space by unitary or anti-unitary operators. And since, and now notice, I cannot have anti-unitary operators because anti-unitary operator would change the sign of f. Because if you put anti-unitary operator here, there's complex conjugation. Complex conjugation will flip the wedge, and therefore I get minus sign. Okay? So necessarily, use of Q has to be unitary. Okay, so because of that, the lifted unitaries will actually form not necessarily a representation of translation group, but they can form a projective unitary representation of translation group. Okay, so this is kind of related to a question that was asked before, but it's slightly different. So what will happen is that it's okay that I act first with translation K2 and act with K1. This can be the same as acting with the sum, but since I'm at the level of quantum states, they are defined up to phases, so I am allowed to have this phase factor here, okay? And so projective unitary representations of R2, they are essentially, they are unitary representations of certain central extensions, G of R2 by U1, which fit nicely into this short exact sequence of groups, where you here, well, this is exact sequence. And as a set, I have the product of R2 by the circle group, but as the product law is shifted by that co-cycle that appeared there. Okay, so first factor is just ordinary group law. Second factor is product with this. Okay, very nice. So central extension of R2 are determined up to isomorphism by what is called the commutator, which is the ratio of psi of K1, K2, and it's flipping K1 and K2. And you can show by the properties that these psi's have to satisfy that this actually can be written in terms of a bilinear skew-symmetric linear map. And this is a bit jargon because basically in 2 dimensions it's just this. You have a number, a real number, and you have the canonical symplectic structure in R2. Okay? So that's it. So now we have this free parameter D. And if D is non-vanishing, then G is called the Heisenberg group. Okay? Let me just continue. Once a concrete realization of psi for a given commutator S is giving rise to group G, all other realizations differ by an exact cochain, meaning that there is some smooth function G sub K such that this holds. And this gives this relation is just isomorphism of central extensions. A concrete realization is given. I chose one which is I'm more comfortable with. Everyone chooses a different gauge. I chose this one. You choose your favorite one. And once you have that, we can observe that if D is equal to 0, this essentially says that the group G is a direct product of groups. So D different from 0 is measuring the twist. And now there's this beautiful celebrated Stone von Neumann theorem, which tells you that the Heisenberg group G has unique up to isomorphism, unitary irreducible representation, which is specified by this Hilbert space, square integrable functions in the line, for which U1 acts in this standard form. And this is the concrete realization, okay, for the gauge I chose. And this is essentially the standard Hilbert space of a particle moving in one dimension, for which the momentum is given by that, and the commutation relations of position and momentum. Position here is q, but it's not real position. This is an abstract degree of freedom. They satisfy this commutation relation. So you see that that d is like an effective Planck constant that appears, okay? And we will see that D has to be constrained. Sorry. Now let us construct such flat Kähler bands. So the first thing we do is we can build a translation invariant Bloch wave function by acting on a fixed fiducial state by this Heisenberg group action. But this is not enough, because if I just naively do this construction, this will not be holomorphic in K. And so I have another constraint. And if I use that constraint, well, first I do some manipulation. I can show that use of K can be written like that. And then I use a Baker-Campbell-Hausdorff equality to show that it can be written like that, because of the commutation relation of P and Q. This should be a Q, actually, it's an X, it's wrong. And then I can introduce creation and annihilation operators, like that. And they satisfy canonical commutation relations. And using this, I can show that the holomorphicity condition is equivalent to requiring that U0 is annihilated by the annihilation operator. Okay? So U0 is actually the vacuum of this bosonic mode. Explicitly, if you write down the solution of this equation, you'll find that U0 has this form. And now note that since tau is in the upper half space, D is also constrained. It cannot be anything if I want U0 to be in L2. And so D has to be negative. And so what we find up until now is that use of K has to be of this form. U0 is the vacuum of bosonic mode A tau. And what you find is that use of K is a bosonic coherent state, because use of K is a displacement operator for bosonic mode. Okay? This is quite fascinating. It was kind of fascinating for me. Okay. Furthermore, remember that in the use of K we had line bundle. So that will give us another constraint. So since use of K must determine line bundle over Brillouin zone, we can see that by simple translation of this and using the projectivity of representation, you can find what the multipliers of line bundle are. And the multipliers are given by this. And then you can kind of guess that D has to be related to Chern number. And how do you see this? Well, you just write a connection and curvature which are consistent with system of multipliers. Consistency just means that that it transforms like a gauge connection, right? You find compatible connection and you take exterior derivative, and what you find is that D has to be minus 2 pi times the Chern. Okay? So this is a very nice result. And you can also find, I think I'm probably reaching the end of my time, but you can find explicit form of wave function by decomposing L2 sub R in in irreducibles of translation of the lattice, because you see in this Heisenberg group, I failed to tell you that there is a subgroup of reciprocal lattice translations, and this is really not central extension, it's really a unitary irrep. And there is this transformation that allows you to retrieve this factor here, is Bloch-Zag transform, which simply sums over the action of UG and weights by character of lattice, and you can see that this F of R has the correct transformation law. And actually, it's actually more pretty than that. F of R determines a square integrable section of a certain Hilbert bundle over unit cell torus. So this U sub k had some line bundle over Brillouin zone imprinted in it. But now here, this, there's a new bundle appearing, not over Brillouin zone, but over this unit cell, where you identify points in the unit cell that differ by lattice translations. So this is kind of related to Poincaré bundle, but anyways. And actually, you can, the fiber of this Hilbert bundle is H of R, and it's a space which is spanned by C linear independent distributions, which I write here for your convenience. And actually, you can show by methods of geometric quantization that this H of R is actually isomorphic to the space of square integrable section, holomorphic sections of this L sub R. So this Hilbert bundle is the bundle whose fiber is H0 of L sub R. Okay. Okay, so if you apply, I'm not going to do this because I don't have time, but if you apply the Bloch-Zag transform to U sub k, you will find that the coefficients can be written like this, using the delta alphas, which are essentially, they are a global frame field for H, multi-valued, because H is a non-trivial vector bundle, but you can write them like this. And for C equals to 1, this is nothing but the lowest Landau level Bloch wave function. And for C greater than 1, it determines so-called color entangled Landau level type wave functions. Sorry?
What's that?
Sorry?
Well, all these notions I'm not familiar with. I don't know what the color entangled Landau level type wave function is.
So this is some kind of generalization of the lowest Landau level.
But does it appear somewhere in the real world, or is it just a mathematical?
I've seen it in some papers, and I think it also appears recently in this twisted multi-layer graphene applications. So it's becoming right here it appears like abstract construction, but I think it can find interesting applications. Okay,
It's if you take a Landau level on the torus with fluxes, and you call X and Y fluxes, and Z you call the current on the torus, these are Landau levels on the torus. Left Landau level on the torus.
So you're shifting the roles of X and
These are
K.
exactly different. But in your world, this is
It's opposite.
yeah, different.
Interesting. So there's another feature that I want to just say, is that the unitary reducible representation of Heisenberg group is unique up to unitary isomorphism. And because of that, this isomorphism will be an intertwiner, and in particular it will preserve the quantum number R. Because of that, that means we can do real space gauge transformations like that. We're allowed, so this is a degree of freedom that we have. And besides, as I said before, we can also do momentum space gauge transformations. So we have these two degrees of freedom. So if someone gives you a wave function, you can do these two transformations without spoiling. So this is just summary. So what I just did in this talk is that upon fixing flat complex structure in Brillouin zone, parameterized by modular parameter, fixed Chern number C, then flat Kähler bands are essentially unique. So that's the summary. I think I made it. Okay.
Hi, Bruno. Nice talk. So in the last part, you discussed when you discussed the flat Kähler band by assuming uniformness on both complex structure, curvature, and metric, you discussed the Heisenberg group. My question is, what's the necessary the key ingredient for the Heisenberg group? So I think even without assuming the fatness of the curvature and metric, only assuming the fatness of the complex structure, you can define Heisenberg.
Yeah. So the Heisenberg group exists once you have these bundles that are going around. What I think that can change, because I've also read your recent paper, and there was something that I still don't completely understand. But if the way you can go back to the Heisenberg group is by modifying the Hilbert space structure and making it k-dependent. And with that, you can cancel the fluctuation of G and F. So they fluctuate in tune because of the Kähler relation, and with that you can get rid of, so yeah, you can have, so I think in particular this construction also holds in that case, but you have to take into account that inner product use of K in H. So it actually, when you do that, I think you no longer have this same notion of Bloch wave function where I said I fix a Hilbert space, but you have instead, for each K, you have a Hilbert space H of K. I think that's the difference.
My second question is, so here the talk is focused on the line bundles. Do you have any comments on the holomorphic vector bundles?
That's a very good question. So I thought a bit about that, my comment is I have two answers for that. One is the case in which you can always recover this case if you consider, so if you have vector bundle, you can consider the highest exterior power of that, because the quantum geometry ultimately is constructed from this, which is a property of the determinant bundle. So maybe I can just say some words of that. So the projector maps you in that case. So if you have a higher rank, let's say rank R, so if it's not a non-degenerate band, but you have some rank in it, you have a map to that. But and over that you also have a tautological vector bundle, which is a rank R vector bundle. But again, the Kähler structure here is induced from the highest exterior power of that bundle. And so when you do that, you kind of are reduced to this case somehow. But again, I'm not completely confident, because then the natural thing to consider would be not central extensions, but things like that, and I don't know. It's the non-abelian case. It's still a bit tricky to me. So my answer is, if you just care about ground state properties when you fill the whole of the non-degenerate band, then okay. But if you care about the non-abelian structure, then I don't know. Yes.
Okay, we have actually lunch which begins at 12:30. So let's thank Bruno again.